y. And how are we going to solve for y? Well, we need to take one of the two equations. Let's take the top equation. Let's flip the easel over and take the top equation, which was 4x plus 3y equals 21. Again, I go back to the original equation. Okay? And I know that x is 3. So 4 times 3 is 12 plus 3y equals 21. Again, as always, my goal is to get an equation with one variable, one letter. I subtract 12. 3y equals 9. Y equals 3. So I have my answer. My answer is x equals 3, y equals 3, which is written as an ordered pair. And now I need to check. Since I've used the first original equation to solve for y, I'll just check in the second original equation. And what was that second original equation? That was 7x plus 2y equals 27. Now, I am writing this down again only because I flipped over the page of the easel. Obviously, if you're doing this on a sheet of paper, you'd already have this equation. There's no need to write it a second time. Let's see. X is 3. 7 times 3 is 21. 2 times 3, because y is 3 also, is 6. And 21 plus 6, indeed, is 27. It does check. It does check. So we have a situation where, interesting enough, our answer, x and y, is the same. Does that make a difference? Obviously not. But if we graph these two equations, if we graph 4x plus 3y equals 21, and we graphed 7x plus 2y equals 27, what would we get? We'd get two lines that crossed. And where would they cross? At 3, 3, at that point. Now, what happens also is we know that 3x equals 3 and y equals 3 are the only two values of x and y that allow us to plug the numbers into these two equations, and the equation works. That is, we know that 21 plus 6 equals 27, and over here 12 plus 9 would equal 21. Any other values of x and y, even values close to 3, for example, if you tried x equals 3.1 and y equals 3.1, or x equals 2.8 and y equals 4, anything like that, it would not work in both equations. You might find, and I'm sure there's plenty of numbers that would work in this equation. That is, you plug in the x, you plug in the y, and you get 21. But when you plug those two numbers in the second equation, it would not work, because the solution to a system of two linear equations can only be one value of x or y. Now, let me amend that statement. If there is a solution, if there's an intersection point, there's only one intersection point. There are two other situations. Let's take a look over here on the easel. Remember, we talked about graphing lines. We talked about parallel lines. What if we had two lines that were parallel? Where would they intersect? Well, by definition, they would never intersect. So if you found two lines that were parallel, there would be no intersection. There would be no value of x or y that matched up, that worked in both equations. There's no solution. How would you know if two lines were parallel if you couldn't graph them? Well, let's go back in our thinking to when we learned about parallel lines. We said parallel lines have the same slope. So, if I had two equations and I happened to get them in y equals mx plus b form, so I knew the slope of each, and the slopes were identical, then I would probably know they were parallel. Why do I say probably? Well, what if they both had the same slope and they both had the same y-intercept? They wouldn't be parallel, they'd be the same line. And if we have two lines that are really the same, and we could write them differently, but they're really the same line, we get it down to slope-intercept form, they're the same line, then we say there's an infinite number of solutions. These are the two situations where you don't get just one solution. You can have parallel lines, that is, the two lines have the same slope, but a different y-intercept. They never cross, there's no solution. Or you have two lines, trick problem really, that really turn out to be the same line, infinite number of solutions. But in general, In general, when we solve a system of two equations, what we have is one intersection point. And that intersection point can be solved in one of the four ways: graphing, substitution, addition, or the elimination of one letter. The elimination method, what we've done in this lesson, always works. I mean, if you do it right, you're going to get the right answer. If there's fractions involved, it's because you can't help it. That is, the answers could be fractions. But in terms of the coefficients, you should always have nice integers to work with. To ensure that you can do this, what we're going to do is take a look at a problem that I've prepared. And again, as we've done in the past on some other lessons, I'm going to put the problem on the board. And after I put the problem on the board and discuss what I want you to do, then I would suggest that you stop the tape, work the problem, turn the tape back on, and I'll be sitting here waiting to give you the answer. Okay? Let's take a look at those problems. Let's go to the board here. I guess we need to erase this old stuff. And here are the two equations. 5x minus 3y equals 7, and 8x minus 7y equals 20. Two equations, two variables. I don't think we want to graph them. I don't think we want to use substitution. I know we can't add them and get one equation. We cannot eliminate because 5 and 8 is 13 and 7 plus 3 is 10. But we need to eliminate one of the variables and solve. So what I'd like you to do now is, after you've written these two equations down, to stop the tape, solve, check, turn the tape back on. I will solve it and check it, and hopefully we'll have the same answer. Okay, hopefully you've solved the problem. Or perhaps at least you've tried to solve the problem, and maybe you ran into a bit of difficulty. What I want you to notice about this problem is that we have numbers that have the same sign. In this case, I chose to make both of these negative. A little bit different than the previous problem, but the same idea. We need to eliminate. Again, I choose to eliminate the y's because they're smaller numbers, 3 and 7 as opposed to 5 and 8. Could you have eliminated the x's? Yes. If you had done it correctly, you'll get the same answer that I'm going to get. So let's see. Let's multiply the top by 7 and the bottom by 3, because that would give us 21. Now we need to change one of the signs. And remember, if I don't want to work with negatives, I need to kind of do a little planning ahead of time. Well, let's see. 3 times 8 is 24. 7 times 5 is 35. So if I leave this as positive and change this to a negative, I'll have a positive coefficient for x in the equation I'll use to solve. So, thinking about that, let me go ahead and make that a negative. So I'm going to multiply the top equation by positive 7 and the bottom equation by negative 3. The first equation is 35x minus 21y equals 49. Then we have, let's see, we have negative 3 times 8, negative 24x, negative times positive 21y, and that's good because we can see that they will cancel each other out when we add them up. But don't forget that negative 3 times 20 is negative 60. Adding up, 35 minus 24, I believe, is 11. And 49 minus 60 is negative 11. And again, I have a negative, but I prefer, if I'm going to have a negative, have it over here and not in front of the coefficient, because I'm going to divide by 11. And of course, by dividing both sides by 11, I get x equals to negative 1. Now I'm going to go back to, which equation? Doesn't really make a difference. I'll go back to this equation here, 5x minus 3y equals 7, and replace x with negative 1. And what I get is negative 5, that is 5 times negative 1, minus 3y equals 7. And of course, bringing the negative 5 over by adding it, I get negative 3y equals 12. And dividing both sides by negative 3, I get that y equals negative 4. Y equals negative 4. So there's my solution. Also in this problem, both answers were negative, just to show you that indeed we can have two answers that are negative. And indeed, if we graph these two original equations, those two lines would intersect. They would intersect at -1, -4. And -1 and -4 are the only values of x and y that will work in both equations. We've shown that's true here. That is, in the original equation we used to solve for y, we need to check in this right here. So let me go ahead and erase some of these things. And again, if you've missed something, the great thing about videotape is you can rewind it, maybe go backwards, and start again and look at it again. Well, let's see. Take the original equation and replace the x with -1, the y with -4. -7 times -4 is plus 28, and it certainly does check. -8 plus 28 equals 20. So, if you were able to do that problem successfully, you should have no problem in solving systems of equation by elimination. And if indeed you have the choice, certainly that's the best method to use. The one thing I should say that can occur is in all the problems I've presented for you, the x's and the y's and the equals and the numbers were lined up. If for some reason you have, let's say the x was over here, all you need to do is bring it back so the x's, the y's, the equals, and the numbers are lined up. If you do that, you'll get the right answer. If you check, you'll know you have the right answer. And this, of course, is leading us up to something bigger and better. In the next lesson, lesson 12, we'll discuss solving 3 equations with 3 variables and also look at systems of inequalities.